All right, so I believe we're recording again. Okay, so this is where it took me. So once I clicked on that link, I signed in, and then I got this. This is sort of the dashboard. Um, you can go to home directory, and you should get something like this. For everyone? Huh? For you? Who tried it? Did that happen to everyone? No one got this? Oh, you got it. All right, great. Um, I'm pretty sure I did this, but I will double check then. So you should have gotten this. Okay. Um, yeah, you're seeing it there. That's Scholar. Essentially, you can open a terminal by doing something like this. Can you send me that error you got? Like, take a screenshot of it and just email it to me. Okay. All right. So this is the terminal. You can type commands on here like my quota, different things like that. Okay. And then what I would do is I would go to something like this and select Jupyter Notebook. And then when that happens, it takes me to this window. And then in this window, as you can see, you're going to go into the queuing system. So I'll select GPU. There are other options, but if you want a GPU, you really want to pick this one. I'm going to have, excuse me, 4 hours. I think you can only pick one GPU right now. You can choose Jupyter Lab or not. And you click on launch. And then it's in the queue, it's waiting. So you kind of have to wait until you get one. And sometimes it can take forever. As you can see, it's taking a while. But eventually you should get your GPU and you can start the session. Oh, there it is. So I connected Jupyter. As you can see, so if I click on one of these, now I have a Jupyter. So it's essentially as what we've been doing in class, just that now this would be running on a GPU in the cloud. Got it? All right. So unfortunately, it seems like bad news. Like most of you were not able to get here. No one. So none of you. Sashi? Huh? How about you? Did you get, or also you didn't get in? Mm-hmm. On the GPU? Oh, not on the GPU. How about you guys? None of you? And in the back, none of you? It's really strange. How about none of you? Okay. All right. Well, home direct. Okay. I'll have to. Yeah, send me that screenshot if you don't mind. Okay, great. I'll try to figure it out. Sorry about that. But anyway, that's kind of the Scholar service. All right. Anyway, let's move on. We don't need that right now, so we have plenty of time. Yeah, go ahead, please. Do you have Windows or Linux? Okay, so first of all, Google if that supports CUDA libraries. If it does, then you have to probably install the driver for the CUDA libraries, and that's going to be, I'm assuming, either a script or because it's going to vary, I think, depending on your GPU. But I would say I would Google, I have this GPU, how do I install the CUDA libraries? And then it'll give you either I guess an exe that you double click on, or it'll be a script that you run and it'll download the proper driver. And then once that happens, that's it, because that's all you need to have. Then when you go to install, you install Anaconda, and then when you're installing on the Anaconda prompt PyTorch by default should detect the GPU. That's the key thing. It's gonna look for it. If it's there, then it'll probably download the correct version of PyTorch for GPU. Otherwise, you end up just running PyTorch for CPU. But the problem then is it's not fast enough.
Yeah.
Yeah. Does that make sense?
Yes.
Yeah, so it's easy actually today, as long as it detects the GPU, which means I think having the driver. I've always installed it on Linux, so I don't know on Windows. But... Any other questions, guys? Yeah, so just search it a little bit. It's not hard. I can tell you that especially today, it wouldn't be that. Right. Great. But yeah, we don't need it right now, and I'll figure out what's going on. Once if you do get a GPU, notice that I've locked in this GPU for 4 hours. I don't need it, so I'm gonna just delete it so that someone else can use it, because as I said, it's a queuing system for the university. All right, so I'm gonna close this. All right, so today then, so we talked, I kind of motivated that we're moving into big data, state-of-the-art things. What we're gonna use now is PyTorch. Now, one nice thing about this is you write, whether you're using a CPU or a GPU, the code that you write is the same. All right, so you don't have to change the code based on the device that you're using. Now, if you are coding in C and with CUDA, then yeah, you're programming in a different way than you normally do. You have to know how to program in parallel, but that's why PyTorch was invented, so that we didn't have to learn those low-level parallel techniques in programming, and instead we just code as we normally do, sequentially, essentially. And so that's what we're going to talk about today, is a little bit of PyTorch. So let's get started. So I'm going to go to the class 65. All right, so this is GPU Scholar. We have covered KNN, the perceptron, Hopfield networks. That was the last topic. And now I'm going to the classic iris torch to motivate NNs. So you can see sometimes I'll say torch or PyTorch, but I mean the exact same thing. All right, so this is where we are. So have some links here. So we'll go through those materials, okay? So let's take a look. So this code provides, so this is a lot of examples of PyTorch. Some notes. This is some matrix multiplication examples that we're going to look at, just some background in Torch. We'll cover that. And attention map mall. So just some additional examples. This is a little bit like those tensor operations, just more specific. And at least, actually, some of these you may have already done when you practice those 70 or so problems. All right, so let's go to table of contents here. And I'm going to add 2 links. So the code that we're going to work on today is here. So I'm going to go to the GitHub, this, and they're going to be under this one. So it's chapter 4. And specifically, we're going to work on this example today, classification with iris. But let me copy the whole repo. Create a link call it repo. Torch. All right. So that has been added. Okay. And then the other thing I'm going to add here is the link to my notes. So read through this. I had already provided this, but it should be here. And it is this one. So chapter 4. This is my whole discussion, like everything on neural networks and deep learning, all right? From neural networks all the way to deep learning, but in Torch, in PyTorch. So essentially everything that we're gonna do, you can see it starts with Iris. So it's the examples that I'm starting with today. Then we're gonna go through linear regression, theory and intuition of linear regression. As you can see, it's familiar. How you build a neural network, the linear regression with another data set called the wine quality data set. I'm going to do that one too. That's already in the repo, and the code is provided here, and I've described it in as much detail as I could think of. We're going to cover this, the correlation matrix, and as you can see, all the steps in the programs, metrics for measuring performance, then linear regression to logistic regression and neural networks. So how it goes from linear regression to something called logistic regression. We're going to see that they're very similar, but there's just one little change. But what's great about this, if you remember on the exam, in linear regression, you predict real valued numbers like quantities, and then in classification, we predict discrete values, right? So that's essentially linear regression is regression values, and then logistic regression is classification. So how do we go from one to the other? And then once we do that, then how do we go to neural networks? Okay, so I'm going to build up on that. Instantiating different models, reading data in batches. So now that we have big data, we can't really feed all the data to the model all at once. So instead, you think of it like a train, right? Those old trains that use charcoal, right? So you'd have to take like a shovel and put in a little bit in the furnace and then a little bit more and a little bit more. That's the analogy of how we feed data into the AI models now. Okay. So then we're going to talk about the terminology. What is logistic regression? This discussion is actually very important because here I introduce cross entropy. So we're going to talk about that, one of the most important loss functions. Okay, so theory and intuition of logistic regression. So read through all this, please. This is very fundamental stuff. We're going to talk about binary cross entropy. Actually, I start at entropy. There should be a link here. It's somewhere there. But yeah, binary cross entropy, multi-class entropy, logistic regression, wine quality. Then we start getting, as you can see, this is a multi-layer perceptron, MLP. This is a deep neural network. And the only difference is essentially that it's got one more layer, right? So, oh, here it is. So intuition of adding more layers, so going deep. And then easy deep learning. And a more challenging problem with the wine quality data set. Yeah, until the summary. There should have been a link here on cross entropy. I may have missed it. All right, I'll add it if I have to. But anyway, these are your notes, okay? So for the next 4 to 5 weeks, this is what you need to read, okay? And I'll be covering essentially this material here. All right, so I'm going to add this link. Of course, I may add a few things here and there, but I'll add this. I'll just say notes. Actually, let me go back to topic notes. All right, so that has been. All right. So yeah, so that's, you have a lot of reading material and you have a lot of examples for the next few weeks. And this is the whole sequence on neural networks until deep learning. All right, so let's get started. So the first thing I'm going to do is focus on one program that demos kind of everything, all the steps. And this should be our first use of PyTorch. We're going to train a simple neural network or some simple thing to perform classification, just like you did with Weka or whatever programs we've used in the past, right? I think KNN maybe also used Iris. So with KNN, we built a model to perform classification of iris flowers. So now we're going to do the exact same thing, but using the PyTorch framework. Okay, so let me close this too. All right, so let's get started. So I'm gonna. All right, it's gonna be this one. So classification, PyTorch, iris. Okay, so first thing we do, we start our Jupyter notebook. It's gonna be prompt. I'm gonna cd into desktop. Okay. List. I'm gonna activate. It seems to be Pi 37. 2025. Yes. 365. All right. Oh, dir cd its 365 2025. Right. All right. Oh, yeah. It's Linux. Okay. So the next thing I'm going to do is I'm going to create a folder. I'm going to call it PyTorch or my PyTorch or something like that, as all of these are now going to be using the PyTorch library. So I'm going to do mkdir my PyTorch. Yeah. And then I'm going to cd into that. Oops. Oops, I have it. All right. So yeah, so here we are. At this point, let's start our Jupyter notebook. So this is the library that I use to teach most of my classes. We have after 365, I have this other machine learning course that teaches more advanced algorithms, like the code, the algorithm for GPTs, for instance, right? So like essentially you want to know how to build your chat GPT. And the language that I use for that is PyTorch, like essentially this exact same one. All right. And then after that, we use even more advanced libraries like Hugging Face transformers, whatever it is. But those are just wrappers around PyTorch or wrappers around TensorFlow. So these are the two powerhouses, okay, at least currently. Now, keep in mind, these things change really quickly, right? I started with TensorFlow 1 in 2015, and around 3 years ago, I switched to PyTorch, and I'm pretty happy with it. But, at some point, they'll make some innovation, and you just have to keep up, right? So the way all of this works is, of course, there's CPUs and GPUs, and that is central to the problem, right? So you guys know how to program with CPUs. CPUs are sequential in nature, so they're not really designed to do things in parallel. Nowadays, you can get computers that have multiple CPUs, and so that's a way of implementing things in parallel, but they just don't have the same power as a GPU. A GPU has, thousands of cores that perform parallel operations, okay? So the problem with a lot of data and really deep neural networks is that it takes a very long time to train them. If you're just using a CPU, that's going to be very slow. As you have learned in the class, one of the things that you have to learn is how to do matrix multiplications, right? You don't have to know the whole of linear algebra, but you do have to know some of these algorithms that allow you to perform efficient operations on the data, because those operations are parallel, okay? So I'll give you like my little story of how, I did this. In I programmed machine learning algorithms on CPUs up until like 2013 or so. And then after that, we got GPUs in 2007 that supported the CUDA libraries, right? And I started learning CUDA, right? Sometime around 2013, 2014, which meant I had to, and that was done in C, C++. So I had to write C, C++ code using the CUDA library, and I had to learn how to program in parallel. That's a very good skill to have today. The people that know how to do that earn like $800,000 a year if you're really good at that. I mean, it's hard, but well worth it. But anyway, not everybody wanted to do that, right? They felt that it required too much work, too hard or something like that, I guess. And so companies like Google and Meta decided that they needed a more efficient approach. So of course, Python, right? So Python, as you probably know, is essentially an interface to C, C++, right? So the code that runs in the background in these libraries is just C code, executables, right? But you're interfacing with it through Python. So they created this library called PyTorch or TensorFlow. And essentially, the idea was, how do we create a programming style that will work in both the CPU and the GPU without change? Now, that's the key thing. Like, you guys will write your code on your laptop for C, and then you can port it to your GPU, and it'll just run almost exactly the same. Okay. So that's really what people wanted. And so they created this idea of creating computational graphs. So that's essentially what's happening in the background, is that you're creating, when you're using PyTorch and you're writing your code, what you're really creating is, in the background, this computational graph. You're like, imagine a graph that you're putting together data and operations, and things flow in one direction, okay? You just don't do that manually. You just code normally, but that's what's going to happen in the background, okay? And then at some point, you just run that computational graph, but it'll run on the libraries on C compiled code. Does that make sense? Guys, any questions about that? That's essentially, so what we're going to learn is how to write code in Python using PyTorch, right? But just keep in mind, in the background, you're creating this computational graph where you're saying, this is data, this is an operations. For instance, this is a matrix multiplication between this data, and it'll produce this. And remember also, I gave you this idea that you have to calculate the gradients, right? which we talked about a little bit. You know, remember that idea in the perceptron of updating the weights? That's exactly what we're doing here, right? And so we have to calculate the derivative of something, right, in the graph, but the PyTorch takes care of that for us. So we just kind of have to design the whole architecture of our network, and then when we run it, PyTorch handles a lot of that for us. Okay? All right, so let's get started then. That gives us a little bit of the background, and we can come back to it later. But let's get to it. All right, so I'm going to click on Python 3. Run there. Okay. So like I said, the purpose of today is really just to build our first PyTorch neural net for the iris dataset, which we're all familiar with already. Obviously, the main library that I want to try out is Torch, right? So I'm going to do import Torch and see if I already have this library. All right, so I'm going to run it. And I believe at the beginning of the semester I installed it. If not, we would have to install it. But this is what does everything. That little torch is going to bring in all the elements that we need for us to create our neural networks. Okay, great. So it ran just fine. So now I'm just going to follow this example, right, which I said is called classification DLA PyTorch iris. Okay, so we're looking at the iris data set. I have a few libraries here that I installed. So MLXten is a nice library for visualization. So we might use that one. These two are really nice. So you know how you guys in your homework assignment for the perceptron, right? You're using what? PyScript, correct? You remember that you're using PyScript to create a website. So whenever you're writing a program from scratch in NumPy, such as the perceptron, you can use something like PyScript, and then you can deploy your website using something like GitHub Pages to the internet. But for something like Torch, for a model like Torch, you can't do that. Instead, we have to use a library called Onyx. Okay, so we're going to learn at some point when you build your models with PyTorch that you can also deploy them to the web using GitHub Pages. The only difference is we're just going to have to learn to use the Onyx framework, which I think the most advanced version of it right now is Onyx Runtime. All right. And so essentially, it's going to be something like you'll create the model, you'll train it, and then you're going to save that model as an Onyx file. And then that file, as long as it's not larger than 25 megabytes, you should be able to upload it to GitHub. And then from your website, you're going to import that Onyx file and then, you know, do your whatever classification or regression or so on. So you can expect that there will be another homework later in the semester where I ask you to train a model with PyTorch and to deploy it to the web using Onyx Runtime. Make sense? Any questions? All right, great. So we'll install those libraries as we need to, as needed. So let's go ahead and start adding the libraries now. So I'm going to do this. I'm going to change the name of this one. Since you guys want me to provide the in-class examples, I'm going to call this one in-class. And when we finish it, I will add it to that 2025 folder. So this is in-class Torch iris, okay? So my goal for today is just to build our first neural network, or our first actually model, let's call it, with PyTorch, okay? Later on, I'm going to differentiate between what is a linear regression model, a logistic regression model, a multi-layer perceptron, or a deep learning, right? But for now, it's just getting that whole pipeline going, and then we can just, you'll see how it's easy to remove one architecture and provide another one, because all that matters in an architecture is that the input and the output is the same, and what's in between, you know, we can replace and call it whatever it is. All right, so the libraries are going to be NumPy, Torch, the pandas library, which you guys have used in 265, sklearn, which we have used. We're still going to be using sklearn for things like splitting the data and things like that, random if needed. And then here, these are 3 new lines of code that we're adding for Torch. So Torch NN, that allows you to create architecture. So we're going to use something from object-oriented programming, which you guys are familiar with, called class inheritance, right? So we're going to instantiate our neural network classes like I did in the Hopfield networks example, but we're going to provide the NN module so that we have a lot of standard functions and variables for creating neural networks from Torch, okay? And then we're just going to modify them. Another one that we're going to need is this one called torchnn.functional. This module provides the loss function. So to give you an example, when we did the perceptron, the loss function was this thing that I derived with calculus, if you remember, that allowed us to create the update rule, right? So you guys remember the update rule in the perceptron. So we are now going to use this more sophisticated mechanism to bring in better loss functions, right? So something called cross entropy or something called MSE. So those two are going to be our big loss functions going forward. I will make a very detailed lecture on cross entropy, where we will start with like flipping a coin, entropy, and lead up to multi-class cross entropy. What's really great about that, actually, when you're looking at neural networks, is that you see MSE and then cross entropy, and then you start to like panic and think, oh my, how many of these loss functions do I have to learn and understand? But actually, there's only 2, essentially. So MSE, which is for the regression data, and cross entropy for classification. Even ChatGPT is trained on a cross entropy loss function. So it's like super important, okay? So I'll spend a big lecture on that. And it's one of the main topics, actually. And then Optim, Torch Optim, is the optimizer. So this is the the stochastic gradient descent, what does the derivatives for us, and all that. Remember again, what are you doing? You're learning this style of programming, right, through PyTorch that allows you to do 2 things: to create a computational graph, which is data, operation, result, data, operation, and so on, building that whole thing in memory, right? So we're learning how to do that. And also that in the background, when you're deploying this on a GPU, the GPU is going to do these operations in parallel, okay? It's going to do them in parallel, although we don't have to code in parallel. But it is using it in the background with CUDA. All right? So hopefully that made sense. So I'm going to go ahead now and hit run and wait for the libraries. Make sure they all install. All right, great. No issues there. So the next step is we are going to, I have a few other libraries here. That matplotlib, mlxten, which is for plotting. So that's probably the only one that we don't have. So it gave me an error on mlxten. So I'm going to go ahead here and install that library. All right, pip install mlxten. So I'm going to hit run on that one. If you notice, another thing that we're going to learn about, that this is actually really important, guys, that you learn. So in this here in this line, it says from torch.utils.data, import tensor data and data loader. So as the name implies, these are objects that wrap around your data. So what we want to, getting data into Torch can be really hard if you're just like trying to do this manually, or if you learn this procedure, it can be very easy. What you always want to do essentially is convert your data into a Torch data loader. Does that make sense? Because once you convert your data into a Torch data loader, the data loader will handle a lot of things for you. So instead of you having to manually code like 30 lines of code of doing all these steps, the data loader just does it for you. Okay, but you just have to get your data in a specific format and then learn how to load it into the data loader in a specific format. But it's straightforward. Okay, so that is always what you want to do, whether you're using images or whatever it is. You know, even ChatGPT data, you always want to put it in a data loader. Okay. Not, you know, the whole X and Y thing does not change. It's the exact same thing, samples, columns, the features, and you know, all that. So that's all consistent. Okay. So we'll see this handling the data in a little bit. So let's go ahead and run it finished installing. So I'm going to do that. Load the library, or as you can see, it finished this time. So now the libraries have been installed. All right, so let's keep going. As you can see here, I've added XGBoost here. I'm not going to use it today, but remember, this is one of the tools that I still want to show you guys later in the semester. So XGBoost is not a neural network-based machine learning algorithm. Instead, it's what is called a tree-based, like random forest, decision trees. This just happens to be the most powerful of them all. So this is very useful sometimes for some tabular data. So we'll look at it later in the semester. All right, let's add a few other things. Let's add here from sklearn, the metrics essentially. And we still need to do a lecture on metrics as well. Okay, so I'm going to go ahead and run sklearn. Okay, so that ran fine. So now, and I'm going to skip the Onyx part. We'll come back to this later, as I'm not going to show you how to deploy anything today. We'll do that. All right, so a few parameters. I'm going to copy these. And let's take a look at them. So I have here batch size, learning rate, and epochs and epsilon. So learning rate, I think you remember what it was, right? So, you know, I said whenever you're updating the weights, you're going to do whatever they are minus a learning rate times the symbol, whether it's positive or negative, to see if you're going to add or subtract from those weights, right? So the learning rate is just some little value that you're going to either add or subtract from the parameters. In PyTorch, you have the exact same thing. You can see I was playing, you know, it's usually some default value like this one, 0.001. Okay, so that is a parameter that you're going to define. Number of epochs is the number of times that you show all the data to the model, right? So I've given this analogy that, for instance, if you're a little kid and you trip on something, you don't have to trip on that something 1,000 times before you learn not to trip on it, right? But unfortunately, with machine learning, the way it is, the analogy is that it would have to trip on the same thing 1,000 times before it starts to click in its head. Okay, so that's what number of epochs is. So if you have a data set of 70,000 samples, you're going to show all 70,000 samples to the model, essentially, n epochs, like 4,000 times. Okay, the only thing is every time that you show the data to the model, you're going to randomize. Okay, that's a key thing to understand. Does that make sense? So every epoch, you grab all 70,000 samples, randomize them, show them to the model. Then next epoch, grab the data, randomize it, show it to the model. And you do that an epoch times. Too many epochs? Yeah, that's you know what determines that is really the amount of time it takes to process. Like it just depends on the model. Like if I have a model and it's not learning, I'm going to increase the number of epochs. But there's a limit because if it's taking me a day to do one, you know, how many epochs can I actually add to it? So there's what I'm trying to say, actually, to answer your question is there's no, sometimes this is very experimental. It depends on your problem and it depends on your data set, and you just try things. So that's why in the past, I like to do like a competition. So I give you guys a data, everyone gets the same data set, and you're supposed to get, whoever gets the highest F measure wins, right? So then what happens? Students start doing things like this. They're like, okay, I'm doing 4,000 epochs. What if I do 6,000? Right? Does that give me better results? And you could get better results. I don't know. Because at the end of the day, the model is trying different things, and maybe it needs more space to try different things. Does that make sense? Yeah. You can, exactly. So going back to this idea of the competition, if your model is not learning, maybe add another zero, or do either 0.01 or 0.001 or 0.0001. These parameters are things that you change experimentally. These are like the default ones, but it varies depending on the problem. I don't know. So for instance, the original ChatGPT was trained for 3 months, I think, or something like that. So you can train for a very long time. Okay. But yeah. All right. So these terms, so we have n epochs, which is the number of times that we show the data to the model. Remember, though, we randomize it every time. We have the learning rate, which we know is the value that we add or subtract from the parameters, right? And we've seen that already in the perceptron a little bit, right? Okay. Now, this one I think is new, the batch size, right? I don't think I've used this idea of the batch size before. So what is the batch size? So, in the past, we've fed 100 samples to our model, and that was enough. Iris only has 150 samples. But when you're moving to the world of big data, you have millions of samples, right? And so you can't give the model 1.5 million images in one go. You're just going to run out of RAM, essentially. Do you guys see that? So what do you do instead? Instead, they had to invent this new mechanism where you would feed the data to the model in what is called batches. So that's why I give this analogy to you of like those trains in the past, right? They had this boiler or something, and they would shovel coal into it, right? So like shovel a little bit, then more, and so on. So that's essentially the same idea. Imagine that you have all this data and you're just like shoveling some of the data into the model, then another and another. And that's called a batch. And the batches are not that big. So for instance, if you have 70,000 images, you do batches of 32. So you take 32 images, give it to the model, then another 32 images, and give it to the model, and so on. So you're going to have, when we're training these models, 2 for loops. The first for loop is going to be for the epoch. So we're doing 1 epoch. And then the second for loop is going to be for the number of batches. So if we're doing batches of 16 out of 70,000, you can do the math there to see how many iterations you'll end up doing. Does that make sense, guys? That's the batch size, okay? And this also is critical, especially if we do an assignment like CIFAR 10, you guys will see CIFAR 10 is color images. So they're large, and you're building a complex deep neural network. So even if, let's say that you decide that you're going to give the model 256 images at a time, so you set your batch size to be 256. What may end up happening is as you're training, you're going to run out of memory, and your model is going to break. So this is a common problem, and so the answer to that problem is you have to reduce the batch size. So then you go to 64, and you keep trying that, and maybe 64 is still too big, so you go to 32 and so on, until you have enough memory to train the model. Got it? So that's why it's nice, to have a better, you were talking about VRAM actually, right? So that's why it's really nice to have a powerful GPU. So I have, I have a 2080 Ti all the time. I have to cut my batch size to 8 or 4. It just because I just run out of, it's a common thing that I run out of RAM memory. And that's why it's really nice to spend $20,000 and buy an H100 or something. And then you have a very powerful GPU. Got it, guys? So when we start to talk about PyTorch, when we start to talk about big data, we have to really start thinking about RAM, about, processing power. And so a lot of elements come in. And these variables in a way allow you to control for that. They're really important. Okay? To manage your RAM, to manage training, and so on. Okay? All right, so let's run this cell. All right, so let's look at the next thing. Now we're going to read in the data. So in this case, as I said to you guys, I'm going to use the iris data set. So I'm going to copy this. You can get the iris data set from this same GitHub. It should be in here. So if you look, it's this one, iris.csv. So you can click on it and you can see you have our familiar iris data. Okay. So that's going to be, it's a CSV file. So that's where I'm going to start. I think I already have it on my desktop. It's this one. Okay, so iris CSV. I've copied it into my folder. That's essentially all you have to do. So now let's go back here. So it should be able to find the file. So we define a path, iris.csv, and we're just going to use pandas. And from pandas, we're going to use the read CSV function. We give it the path, and then we say that the delimiter for it is comma. It's a CSV comma separated file. And then it should load our data into this pandas data frame called iris raw data. All right, so let's go ahead and run that. All right, no issues. So now the first thing we might want to do is we just look at the pandas data frame. And there you go. That's our data in pandas. As you can see, it's nicely formatted. It shows our familiar. How many features do we have in the iris data set? 4, right? There's 4 features: sepal length, sepal width, petal length, petal width, and then there's the class, which is setosa, virginica, and versicolor. There's 150 samples, okay, and that's our data. So it's, what we have done before. All right, so now the next step is, of course, we're going to change the classes from words to numbers. So setosa will become 0, virginica will become 1, versicolor will become 2. So we can do that with a simple data map in pandas. So you can see here, we're grabbing the data frame and we're saying for the class species, just this one, species, right? We're going to map. And we provide a dictionary of the mapping, okay? So that's transformed now. So if I run it, you can see that now the classes are numbers instead of words. Remember that only Weka handles the strings for you automatically. Otherwise, you have to manually change it. Okay. So the next step is going to be, so we've done this. All right, so now we're going to visualize. So this is part of what we can call data science, right? So you want to visualize your data. You want to, what are some techniques available out there that could help us to get a better understanding of the data set, right? So in this case, I'm going to grab first the headers. So I'm going to create a list of headers here. So I grab the columns, the values for them, and then create a list. And you can see I have them. Okay. Then let's go over here, and I'm going to grab this code, which will create something called a correlation coefficient matrix. And essentially, there's some math involved, but we can just use it as a black box. And we want to understand, though, what this is telling. So that's really important. Okay. So this is the key thing. So let's say you're doing some consulting for some company, Procter and Gamble or something like that. This is something that they would be really interested in, right? They would want to know the correlation between things. Like, are these two variables positively or negatively correlated? Or is there no correlation, right? So those are things that are really important. So for instance, let's say that, what's a good example? Let's go back to housing prices, right? So the housing price would be positively correlated with the number of bedrooms, for instance, right? So, the more bedrooms, the more expensive the house. Number of bathrooms would also have a positive correlation. Do you guys understand? So that's essentially what this is telling you. But it's a nice table, so you can see it shows the variables here as rows and also as columns. So obviously in the diagonal, they have a one positive correlation because it's the same variable. But this is telling us that, for instance, we could say, so the class is species, right? So out of these, there's a negative correlation, if you look, between species and sepal width. So as one goes up, the other one goes down, right? Whereas for the other ones, it's a positive correlation. And the strongest one is between petal length at 0.65 and the species. This correlates into saying that petal length is probably, of all the variables, the most important. Well, actually, this one is 0.61. Okay, yeah, so this is still, because negatively is also important. But this is the most important. Got it, guys? So this is really important, especially if you are looking at a data set for the first time. Let's say you collected some data about whatever it is, and now you get something like this, like a correlation matrix. It starts to give you some insight into the problem. Yeah, go ahead, please. It's based on the data. It's like, this is the physics of the world, and we're capturing it with this matrix. So it means that sepal width, so let's see here. Trying to think. So no correlation would be zero, right? So you can't, let's say, for instance, that species, because this is actually, it might be thinking about this number as, it's not discrete, right? That's your question, right? That species here, it's not thinking about it in terms of being discrete, it's thinking about it probably in terms of it being from 0 to 2, right? So yeah, so this is what that's essentially saying. So actually, looking at species may not be such a good idea because it's a little bit more, because it's discrete. But yeah, you're right. I mean, it's treating it as a number, so it makes it more like a 2 So this one, and then this would make it more towards 0, right? So yeah, so I think it's more intuitive, I guess, to think about it in terms of like sepal length and sepal width, or the features essentially. So because then we could say, let's take petal width. We can say that as petal width goes up, so is sepal width, right? So I agree with you. You're right. And then petal width and sepal width, it's a negative correlation. So as petal width is going up, sepal width is going down. Yeah. So you're right. So because this is a discrete set of values, it's not treating it as a discrete set of values. It's treating it as the value from 0 to 2. Yeah, I agree with you. So it still provides some information, though, some insight into the correlation of the variables, but you just have to be a little bit more careful of your interpretation of it. Yeah, good point, actually. Yeah, go ahead. Say that again. That's right. That's right. That's what it's saying. It's just, yeah, exactly. It's just looking at between any two variables. It's trying to see if as one goes up, the other one goes up, right? So it's the example I was giving us. The number of bedrooms goes up, so is the house, the price of the house. His point was, and he's correct, is that species is actually discrete. It's, 3 classes, and one species 2 is not necessarily more than species 0. They're just different. So, but if you want to interpret it strictly, then it would say that as one goes up, well, in this case, as the species value goes up, then sepal width would be going down. Or as species goes up, sepal length is also going up. That's really what it's telling. So like, what is the impact of one variable versus another? But this is probably better to look at when you're looking at regression type of values. But this is not a regression value. This is a discrete value. Does that make sense? Yeah. So sometimes this can be useful just to, as I said, to give you insight. This is not at all related to the neural network. This is just a technique to kind of compare one set of variables to another set of variables in your data. But this can be very useful. All right. So we did this plot. And this is called a correlation matrix. Let's take a look at. Now we start processing the data. So the data is currently a pandas data frame, right? So we want to convert the data into torch tensors, but initially we're going to convert the pandas data frame into a NumPy array. So if you look here, iris raw data is a pandas data frame, and we use 2 NumPy to convert it into NumPy, which is something that you already understand. Oh yeah, please.
So about that.
About which part?
Well, about converting pandas into a NumPy.
Yeah.
Is that something we always want to do? Like.
Yeah, because it's different data structures. The data is exactly the same, right? So the data was in CSV, then it was in a pandas data structure, then it's in a NumPy data structure, and then it has to be in a torch data structure. Always the same data, but just different data structures underlying.
So what's stopping someone from just going straight from the CSV to NumPy? Is that just not?
It's possible. No, that's possible. That's possible for sure. I just did it because I like preference. So I like to take a CSV and make it into a pandas because I have a lot of power with pandas to do lots of things in a very intuitive and easy way.
Okay, and then when you're ready to start like doing operations on that data, then you switch it over to NumPy?
Exactly. So that's why, since I was going to load it as a correlation matrix and everything, I wanted to I wanted it to be a pandas because it would make my life easier. NumPy is going to lose, for instance, the column names. But if I want to create something like this, I need the column names. Do you see what I'm saying?
Right, yeah.
So right. They're going to be retained in the pandas data frame, but they're lost once you move into the NumPy data structure.
Right.
Yeah. All right, great. So that's what I'm doing now. So I'm just converting it to NumPy. So now it should be a NumPy array. So I'm going to print it. And as you can see, the data is still the exact same, but now the headers, the column names are now gone. Okay. So, but this, if you try to load this NumPy array into Torch, it won't work. So that doesn't, that's a common mistake in the beginning, actually, that you think you can load something in NumPy, Torch will not. You have to convert it to the data structure of Torch. The one thing is that the functions are very easy, right? So we have these simple functions that change from one data structure to the other. And so it shouldn't be that difficult. All right, so I have my data as a NumPy array. Now we start doing, visualizing the shapes. I'm going to go over here. I'm going to run shapes. You can see there's 150 rows and 5 columns. And now we have to use slicing. You guys remember at the very beginning of the semester, you looked at several examples on slicing. So just like in the word problems, we want to arrive at X and Y. You can see that here. I'm going to take the iris raw data NP, and I'm going to grab the first 4 columns for the X data and the last column for the Y data. So given that you guys know how to slice already, right, you understand that this means all rows, and then this means all the columns except for the last one. And then here, this also means all rows, and this just means the last column. Got it? Let's just slice it. We've done before. And this is, again, where doing those first 70 to 100 problems starts to pay off, right? Because it's very similar operations. So I run it. I have them now. So now I can visualize my data. You can see the data there. Okay, then this is something you want to do. If you notice, the data, if you look inside, the data type of each number is what? Float. But these are labels, so you want to convert them to integer. So then you say y as type int, and it just converts the data type to integer, essentially. So I'm going to hit run. And now if I print y, you can see that the numbers are now integers instead of float. Any questions? Make sense? All right. Save it. Now this part I like to do. I like to print the histogram. Now this is also where it's similar to something you did in Weka. If you remember when you loaded your data into Weka, you could see these columns, right, that it created. So I like to do that manually because I like to see the data distribution. If you remember, the point of looking at that histogram is to be able to answer the following question. Is my data balanced or imbalanced? If my data is balanced, then that's very helpful to a machine learning algorithm. But if you have data that's highly imbalanced, then that's going to be a more challenging problem, essentially. Okay. So you always want to look at the histogram of your data. So here, I'm just going to look at what are the unique values in my Y. So there should be 3 unique values, which are 0, 1, and 2. Okay. Then that's my set, essentially. I can look at, print out the number. So there's 3 classes, essentially. And then I'm going to use matplotlib to create a histogram. All right, so basically we give it the Y data, we tell it to automatically give us the bins, and we create our histogram. And as you can see, that's our histogram. We have classes 0, 1, and 2. So if I gave you this graph on the exam and I asked you, is this data set balanced or imbalance? What would you say? Balance, exactly. So that's good. Knowing that tells you, okay, I can expect maybe good results with this model. Later on, when we do the wine quality data set, I've chosen that one because it'll give us an imbalanced data set. So it presents a more challenging problem for us to solve. Got it? Yeah, so we'll see that in a future example, but this just provides the histogram. So we know the data is balanced, okay? So now we can save it, right? And we can proceed. So we can look at the shapes. It's always good to print the shapes. I highly recommend that you do that. So the shapes of X and Y. So you can see 154, 151. So we have our X data and our Y data. All right. Then we're going to do the splitting of the data just like before into the train set and the test set. And this is, we can achieve this with train test. So this is just like before. I think we've done this already. From sklearn, I import this function. I give it X and Y. I specify the test size. So that's 20%. So that means 80% of the samples will be used for training. And this will produce X train, X test, Y train, Y test, which are the subsets of the data set that I need to use to train and test the model. Any questions on this one? Yeah, go ahead.
Random seed. I don't know if we just went over that.
I'm about to.
Okay.
I'm about to talk about that.
I'm gonna ask, is that like a very weak train or is that built into sklearn?
So I have it here. So I'm gonna copy it and I'll explain what that does. So random seed, right? So I can set it as a constant, 42. And if I use, so if this is 42, then every time I run it like that, I'm always going to get the same data set. So it's going to be randomized, but it's always the same. So why do you want to do that sometimes? Replication, right? So you want to replicate your results, right? Then you use a constant. Got it? But actually, it's better to use a random value here. I call this a poor person's tenfold cross-validation. So tenfold cross-validation was something that you used in Weka. If you remember in Weka, you did a thing where you did the split and you said 80%, or you could have selected a bullet that said something like tenfold or 10K fold or something like that. If you remember that. So what happens with tenfold cross-validation is you take your data and you split it into 10 bins. Okay, 10 bins. And then what you do is you're going to run 10 iterations. Every iteration, you grab randomly 9 of the bins and you use those for training. And then the remaining bin you use for testing. You calculate a score, 80% accuracy. Then you repeat the exercise again. Pick 9 of the bins for training, 1 for testing. Gives you a score, this time 78. Third time around, split into the 10 bins, pick 9 of them randomly, train on them, evaluate on the 10th bin, provide a score, 82. You do that 10 times, you take the average. So in this example of 82, 80, and 78, your average is what? 80, right? So 82, 80, 78. You have an accuracy of 80. Why is that good? Because it's not just one isolated run that you did. You actually randomly, shuffle the data and you did 10 repetitions. And sometimes it gave you 82. Sometimes it gave you 78. But essentially, you were able to calculate an average. Do you guys see that? That's what tenfold cross-validation is. You split it into 10 bins. If you only do 42 every time, you're really just looking at it in one randomization, one time. So it's essentially like getting that, let's say you got 82, right? And you're always getting that 82, but you're missing the fact that sometimes actually it can be 80 or 78. You see what I'm saying? So that's what this is for. So, you set this randomly. So every time you run this Jupyter notebook, it's going to try a different randomization as you're training your code. If you run this 10 times, you'll probably get 10 different accuracy scores. But what's good about it is it starts to give you a tendency, right? So you're not just getting one view of it. You're getting multiple views, and essentially you're getting the average value. Yeah.
But when you normally have to share your findings, would you then want to set the random state so that other people can verify that your AI is working independently?
Yeah, in that case, I would say, okay, I ran the tenfold cross-validation. I believe my average is 80, and you report those statistics. And then then I guess you can pick a constant value that gives you something around 80, whatever it is. And then, yeah, you tell them, use this constant value, and you'll get the same score I got, which after I did tenfold cross-validation, this is what the tendency is towards this average. You see that?
Sort of. I think I'm gonna miss what tenfold cross-validation is.
So I just explained that. So tenfold cross-validation is you take the training set and you split it into 10 bins. And then you grab 9 of the bins for training and you leave one out for testing. So because you split it into 10 bins, you're going to do 10 runs. Do you see that?
Yeah.
So that's it. That's what tenfold cross-validation is. It's just different ways of like measuring performance. You definitely don't just want to have like one isolated case. You see, like if you set it to 42, and let's say you're in a competition, right? And you always set this at 42 and you don't change it and you keep running it every day for a month, you always get the same thing essentially, right? And so when you go to the competition, you're like, hey, this is my result. Someone else comes in and they're like, no, it's actually higher. And when you look at the parameters, the only difference is they were randomizing things and you weren't. Right? Do you see that? So that's what this means essentially. Randomization is really important. So let me give you another example why this is relevant. So imagine what's a good example of this? It's not going to show, but can I describe? I didn't install. All right, here we go. Let's take this analogy, right? We learned that in stochastic gradient descent, we had this, we were here, we wanted to go down, not up, correct? You guys remember that idea? Okay. In a neural network, it's not going to look like this. It'll look more like this. Do you see that? What is the objective still, though? You want to get here, right? That's the lowest point. So why do you randomize? Because when you randomize, you're not always starting at the same position. Let's say you always stuck with 42 and you never randomized. What if that meant that you always fell here. What happens there? Every time, and you get stuck there and never come out of that. So in the previous examples, which were very simple neural networks, the objective always looked like this. But now, as we build more complex deep neural networks, it's similar, but it looks more like a mountain range intuitively. I mean, this is literally how it looks. And so the problem when you always start with just pick one value and always stick to it, use a constant of 42. If you fall here, even let's say you fall here. Once you hit that, you're stuck there forever. But if you randomize, every iteration, you have an opportunity. So now you start over here. Okay, you got stuck. You fell over here. Okay, you got stuck. But one time, you were lucky and you started there. And when you start here and you work your way down, then you achieve the greatest reduction in the cost. Remember that this chart is cost. What was here? Do you guys remember? Error. The error, which is in terms of W. Remember that this was the W, the weight for that specific point in time. So the error, as you said, which was y pred minus y, or y pred minus, like that, right? This is a constant. This is in terms of thing that's changing in this thing is that. But if you always use, if you don't randomize, you can essentially, it translates to saying, let's say this W is 3. So then if you start at 5, even though you're decreasing it to about 4.5, you're going to get stuck there and never come out. But if you're randomly picking the values, eventually you might say, let's say this is 4. So once you hit that 4, it'll make its way down to the lowest cost. And that means, because that's this, right? So that means that you achieve the best set of weights that gives you the best model with the best ability to predict. So if you're predicting the stock market, this might mean that you lose $500 that year, but if you get this one, you actually made $1 million because the model is just more precise. Again, this is an idea we've talked about before, right? We're going to keep talking about this idea for a while, for a few weeks. But right now, I'm saying this in the context of the randomization. Why randomization is important. Does that make sense? Any questions, guys? Let's see if I can. I don't think that got recorded in that video. I forgot to install my little board. Questions? All right. But yeah, so you have a follow-up or yeah, what's your question? Go ahead.
To like how much effort the or the like overall performance of the machine learning algorithm? Is it in reference to
you're minimizing the error? So that's what this means. So remember that this equation it was like this, right? And we just said that this is a function that captures behavior that looks like this. When it's squared, we did that example, the square looks like a bowl shape. But the thing is, we write this equation, which is the difference, right? The predicted versus the real. And we're trying to minimize that difference. What do we want actually? We want a model that if this is a 3, this is a 3. If this is a 2, this is a 2. So essentially this is a 0. That's what we want. And this function captures that, right? So we want to minimize this. And it just so happens that this in a graphical way looks like this, where we have a relationship between the W and this value. And we're trying to minimize this value. And the relationship between this value and this value, given this looks like this.
So does cost represent like the zero? Yeah. Oh, okay. Oh, okay. I see why this. Okay, yeah, that makes sense.
We're trying to minimize the error. This is called the loss function or the cost function. But we're essentially trying to minimize. We're trying to develop a model that is as good as the real data. Remember, these are constant values, right? This is 0, 1, and 2 for iris, always. So we want this to also be 0, 1, and 2. And so when you take the difference of them, it's 0. So our goal is to go down to 0. And that's why but we cannot fall. So here's the thing that you might be missing. You cannot fall there or there. That's impossible. There is no universe that holds these or these. The only universe is this one. And what determines this universe? This. That function. So just like here, x2 determined this universe, this function becomes like this when we start building really deep neural networks. It's a little bit more complex in the structure of the graph, but remember, it's capturing the relationship between the cos and the w. As we changed, the only thing we can change is that w and the bias. And we want to change it in such a way that this goes down. Yeah. There's a proof that I have actually of why it looks like this, but let's skip that for now. But a good analogy is to always go back to the quadratic, because you know that if you plot this one, it'll look like that. X squared will look like that. And so this, once you start plugging in a very complex neural network in there, it starts to take the shape. Okay? Like that. Any other questions? Yeah. So that's the objective, as I said. And going back to the randomization is if you want to replicate the same result, great, select a constant, but you can think of it as always falling there. But that's not a good thing. That's not a desirable thing. What we want is random placement. So random, and that's why it's called stochastic gradient descent, right? So there's some random component going on in there. Another way of thinking, imagine this is like a war zone, right? And you want to get to the bad guys here. So you drop a whole bunch of paratroopers. This is another analogy I've heard. So soldier, eventually some of them fall here and they take the base or whatever. See, but it's just, all it has to do is with the how you start or initialize these values, the W's. You don't want to initialize them as zeros or ones. You want to initialize them randomly and so on. And also, that's why you shuffle the data, because that's also something else that helps. Okay? All right, so let's keep going. So I've done, okay, so as I said, instead of selecting 42, what I'm doing here is I'm randomly picking a number, okay? So by picking this number randomly, then now this random seed variable gets assigned here. And so every time I do the split, it's a different split. Okay, so different split. So if you're running this and you run it multiple times, especially with complicated data sets, you'll start to notice that sometimes your F measure is 65. At one time, it went up to 75. So for instance, another example, when I've done the competition in this class, we go, you have to win the trophy, you have to show that you did like several runs and you're showing us the average result, not the best result that you got that one time, then you can't even replicate anymore. See what I'm saying? So this is really important. All right. Okay, so we have our data sets, X-train, and so on. So now let's move on. We can print the shapes. We can print the shapes here. All right, so you can see 120 samples are going to be used for training, 30 samples are going to be used for testing. Okay, so that's, this is the X's, and then these are the Y's, right, corresponding Y's. Okay. Now, one thing that and this is important actually to understand. So let's take a look at this. So X test data type. Float 64. Is that important? So this is actually pretty important. So why? GPT-4, GPT 4.5, DeepSeek, right, have 600 billion parameters. So those models are massive. They're gigabytes of data, right? And if let's say you take one of those pre-trained models and try to fine tune it on your computer, you're just going to run out of RAM memory, essentially. So a new technique that has been created or as part of machine learning is to do something called serialization. So they serialize the data and it's got a term that I can't remember right now. But essentially what they do is they play with the size of the variable. If you have a variable that's float 64, it allocates a specific section in RAM, right? That is of size float 64. So imagine now if you have 600 billion of them. That's a lot of memory. You see that? So a way to get around that problem is to quantization, that's the name. A way to get around that is to change the data type to a smaller one. So hopefully the model will still perform well, even though without having to use such a big variable. So here, for instance, this model will do fine with float 32. And PyTorch, I think, has functions that allow you to take all the variables and change them to float 16 and even float 8. So make them really smaller. Okay, yeah, go ahead. Pardon?
Memory.
Yeah, this is in terms of the amount of memory that you go to float 32. You make it smaller. Yeah. So
change the memory.
Yeah, the values are the same, but they may get truncated or rounded or something like that. But yeah, it's the same data essentially, and you're just changing the structure that holds it, the buffer. Instead of float 64, it's float 32 or float 16 or whatever. Okay, so that's what I'm going to show. So this is probably the last thing we'll do today. If you notice, it's float 64 right now, right? But I'm going to change it to, and the Y's are int 32, right? So I can look at the data type. Now the labels, you don't really have to change them because it's less data, but definitely the X data, you can change it, right? So you can change the data type just so it doesn't take up as much memory. So with Iris, it doesn't matter because Iris is tiny, but when you're using massive data sets, then yes, this is very crucial, very important, okay? So let's try that. So we're going to do the following. You notice I'm taking X train, X test, Y train, Y test, and I'm going to say as type and change the data type to float 32, right? So you can see here, the result was float 64 for the X values. And now I'm going to run this to change it to float 32, essentially allocating less memory for each variable. As far as the integers, as I said, that really doesn't matter. But just to show something, you can convert it to 64. So you can see, so now we can grab the same variable and it should be float 32. There it is. So you quantize the data to make it smaller. And maybe this helps you so that you don't run out of memory when you're training a very large model. Does this make sense, guys? Pretty important technique, actually. All right, so once that's done, the last thing, and we'll stop here for today, and we'll finish this up on Wednesday, is I'm going to convert, now this data is ready to convert to torch, and it's very easy. You just do torch dot from NumPy, grab the NumPy tensors and convert them into torch tensors, and that's it. So you can see we did that. All right, so we're almost ready. I think the next step is to normalize the data and create the data loader. So that's the next thing that we will do on Wednesday. And then we'll start training our neural networks. This pipeline that I'm following today is pretty much what you will use for all your problems, okay? All right, so let's stop here for today, and I'll see you guys on Wednesday.